Okay, this is exercise 1.61 part 4. This is actually a very important example. So if you don't understand it the first time you watch the video, go back and watch it again. Though actually, you should have been doing this before you watched the video. You should have tried doing this before you watched the video. But if you don't understand it after you watch the video, go back and watch the video again. Because like I said, this is an important example. All right, so L is going to be a linear transformation from Rn. L is a linear transformation from Rn to Rm. And it's defined in the following way. So we've got n vectors, u1 through un. These are vectors that are in Rm. And I've already made a typo. That should be an m. Okay. That right there, I did have an n, but it should be an m. So u1 through un are vectors in Rm. And if v represents a generic vector in Rn, L applied to v is given by the formula x1 u1 plus plus x in un. Okay, now using matrix vector multiplication, this is just u1, the matrix whose columns are given by the vectors u1 through un, times the vector x1 through xn. Okay, and another example later on asks you to prove that matrix vector multiplication is a linear function. This basically is going to be proving that. Okay, so I want to prove L is a linear transformation. So I'm just going to say let v1 be the vector whose coordinates are x1 through xn, and v2 is going to be the vector, I'm going to use y1 through yn. Okay, so L applied to c1 v1 plus c2 v2 is equal to L applied to c1 c1 x1 plus c2 y1 all the way down to c1 xn plus c2 yn. And given the formula for L, this is just c1 x1 plus c2 y1 u1 plus plus c1 xn, I'm running out of room, plus c2 yn un. Okay, now I'm going to arrange everything so that I get all of the sort of v1 stuff together and all of the u1 stuff together, or all of the v1 stuff together and all of the v2 stuff together, like I have done in previous videos. So this is just c1 x1 u1 plus plus c1 xn u1 un plus c2 y1 u1 plus plus c2 yn un. Okay, now this top one, this is just equal to c1 times x1 u1 plus plus x in un, and then the bottom is just c2 times y1 u1 plus plus y in un. And that, well, that first thing, this is just c1 in that brackets, that's exactly lv1 plus c2 lv2, that's what's in the second bracket. Okay, so that proves that this is linear because L applied to c1 v1 plus c2 v2 is equal to c1 lv1 plus c2 lv2. Okay, in other words, that proves it's linear. Okay, so just like with problem number 1, I understand that this gets very tedious when there's a bunch of different indices and dimensions and stuff like that going on. Okay, but here's what I think you should do. Go back to the specific case, or go to a specific case, let's say when n is equal to 3, and prove this when n is equal to 3. Okay, so just go through this same exact proof, but for the specific case when n is equal to 3. And I think you'll see it doesn't really matter what m is. I mean, as far as how complicated the proof is or how tedious the proof is with a bunch of indices and stuff, it doesn't really matter what m is, but it does kind of matter what n is. Okay, so just go through this same thing again with n equals 3. And like I said for problem 1, it will either help you understand this if you didn't understand it, or if you do understand it, kind of doing a specific case will kind of check your understanding to make sure that you understood it, to see if you can modify the proof just a little bit in a slightly different scenario. Doing stuff like that will help you check to see if you actually understand it. And if you have any problems, it'll kind of show you where those problems are and you'll be able to work it out.